Hello students, welcome to the class of circuit theory and network. This video has been made for the third sem students of computer science engineering. I am Priyanjali Mukherjee, assistant professor of electrical engineering of Narula Institute of Technology. In this video, we will discuss on the parallel resonance and the PPT contains the parallel resonance, its practical circuit, the dynamic resistance, its properties, variation of circuit parameter with frequency, the quality factor and bandwidth, the examples with the applications. Next is the parallel resonance circuits. Now, the given circuit represents the parallel resonance circuit where the coil is connected parallel with the capacitor and the resistor, and in all is connected across the AC voltage source of variable frequency. So for this circuit, we can say that the total admittance, that is equal to 1 by Z, where Z is the impedance, equal to G plus J omega C plus 1 by J omega L. This G is the conductance, and that is equal to 1 divided by R. Now, from this equation, we can write that Y is equal to G plus J into omega C minus omega L, or G plus J into BC minus BL. Whereas the BC is the capacitive susceptance, and this is equal to 2 pi Fc, and BL is the inductive susceptance, and that is equal to 1 by 2 pi FL. Now, at the resonating condition, the circuit acts as a purely inductive circuit. That means the imaginary part, this J into BC minus BL, will be 0. So we can compare this 2 pi Fc is equal to 1 by 2 pi FL, and for this the Fr represents the resonating frequency, and Fr becomes 1 by 2 pi into root over of Lc. And we know that omega R, that is equal to 2 into pi into Fr, and that is equal to 1 by root over of Lc. And from this equation, we can say that the current is at resonating condition is V divided by R. Now, this one is the practical circuit of parallel resonance, where R and L is connected in series and both are connected in parallel with the capacitor, and whole circuit is connected across the variable voltage supply. Because for any inductance, it has some resistance, and in this case, we are considering this R. So now, the admittance in the branch, this one R and L branch, that is equal to 1 by R plus J omega L, and impedance of the capacitive branch is minus of J omega C, and the admittance is 1 by omega C, J by omega C, and the total admittance is the summation of these admittances of these two branches, and that is equal to it becomes R by R square plus omega L square minus J into omega L by R square plus omega L square minus 1 by omega C. So at resonance, we know that the imaginary part becomes 0. So if the imaginary part becomes 0, then this part, that is equal to XL by R square plus XL square, is equal to 1 by XC, because omega L means XL, and omega L is equal to XL, and this imaginary part equal to 0. So this part omega L by R square plus XL square equal to 1 by omega C, that is 1 by Xc. So from this equation, we can solve that XL into Xc is equal to R square plus XL square, and XL is equal to 1 by 2 pi SL and X is equal to 2 pi Fc. From this equation, we can write here L by C, and that is equal to R square plus 2 pi Fr into L square. Or we can find out the value of Fr, and that becomes 1 by 2 pi L into root over of L by C minus R square. Now, in this case, the resistance value is very small, and as it is very small, so we can neglect this value, and then Fr becomes 1 by 2 pi L into root over of L by C, and that is equal to 1 by 2 pi into root over of 1 by Lc. So, in the series circuit as well as in this parallel circuit, the resonating frequency becomes 1 by 2 pi into root over of 1 by Lc. Next is the dynamic resistance. Now, for the dynamic resistance, first we need to draw the phasor diagram of parallel RLC circuit, parallel AC. So this is the V voltage, and IL, that is the current through the inductor, that will be lagged behind, as there are considering some resistance is there, so it will lag by an angle phi. And for the capacitor, the current is leading from the voltage, so I is in the leading direction, and it is leading by 90 degrees. Now this IL can be divided into two halves. One is IL cos phi, another is IL sin phi. So in resonance, this IC and IL sin phi would have the same magnitude but opposite direction, and hence the IC will cancel this IL sin phi. So we can say that IC is equal to IL into sin phi. Now IC means V divided by XC, whereas the I is the V divided by ZL, and sin phi is the XL by ZL. So it can be written from this diagram, whereas this represents the resistance R, and this is the XC and XL, and this is ZL, and Z is equal to impedance, whereas XL is the inductive reactance and it is capacitive reactance. So sin phi means this XL divided by ZL, whereas the I is the V divided by ZL. So from this equation 7, we can find out that the Z is equal to root over of L by root over of C, and cos phi, that is equal to R by ZL. Now the IL and IL equal to IL cos phi, as this cancel out this I sin phi. IC cancel out this I sin phi, so IL becomes IL into cos phi, and cos phi is equal to R divided by ZL. So we can say I is equal to IL into R by ZL, and I means V by Z equivalent, and that is equal to IL. IL is the V by ZL and R by ZL. So from this equation we can find out that Z equivalent equal to ZL square into 1 by R, and we know Z equivalent is equal to 1 by RC, whereas this Z equivalent is known as the dynamic resistance. And at the resonating frequency, in parallel resonating network, the impedance is completely resistive, and this value of the impedance is known as the dynamic resistance of the parallel circuit. So the dynamic resistance becomes L divided by C into R, and normally R being less, that means the impedance is very high at resonance, and then the current is much lower in the parallel circuit, and hence this circuit is called the rejector circuit. So next is the properties of the parallel RLC resonance circuit, and here also the power factor is unity. That means at resonance it works as the purely resistive circuit. The current at resonance is V by L by CR, and it is in phase with the applied voltage, and the value of the current at resonance is minimum, and hence it is called the rejector circuit. And the name impedance is maximum, that is L by CR. The admittance is also minimum, and the net susceptance is 0 at the resonance. And the resonating frequency of the parallel RLC circuit is FR equal to 1 by 2 pi L into root over of L by C into R square, where we are not neglecting R. And if we neglect the R, then it becomes only 1 by 2 pi L minus into L by C minus R square by L square. And this is the resonance curve of the rejector circuit, where the frequency is increasing. So at the frequency of FR, that the current is the minimum. Next is the variation of circuit parameter with the frequency. Now here the frequency is represented in the x-axis, and if we consider the omega c, then it becomes a straight line. That is the capacitive susceptance BC, that is equal to omega c, and that is equal to 1 by xc. And for the BL, that is 1 by omega L, that is the inductive susceptance, that becomes the hyperbolic curve. And from this graph, we can say that at the resonating frequency Fr, both are same. That means imaginary part BL equal to BC, and the region that is less than the frequency, when the frequency is less than the resonating frequency, then the inductive susceptance has much more higher value than the capacitive susceptance. And for the region above this frequency Fr, then the capacitive susceptance is much more greater than the inductive susceptance. And here the imaginary part is 0, so the admittance equal to R by R square plus XL square, and Z becomes the opposite of Y, that is R square plus XL square by R, and the current equal to V divided by L by CR, where L by CR is the net impedance at resonance of the parallel circuit. And this is the impedance curve, and at the maximum this is the impedance Z. And if we consider two frequencies, the Z at the root over of Z by root 2, and this frequency band of omega 1 to omega 2, this is known as the bandwidth. So this represents the impedance curve versus the current curve. The current curve is the opposite, whereas the impedance curve, that means impedance curve is here, the impedance curve is the maximum, that is the maximum impedance, whereas the time current value is 0. Next is the Q factor of the parallel circuit and the bandwidth. So Q factor is the ratio of the IL or IC to the total current I. So if we consider the IL, then Q is equal to IL by I, and IL is the V into Z equivalent by ZL into V, and that is equal to Z equivalent by ZL, or it can be written as L by RC into root over of C by L, minus that is equal to 1 by R into root over of L by C. And the same expression can be obtained if we consider the capacitor. So IC by I, that is equal to V into Z equivalent by X into V, that is equal to Z equivalent into divided by XC, and it is also becomes 1 by R into root over of L by C. And here if we consider the graph, then we can see that at F1 frequency the value is V by root 2, and for F2 that is also V divided by root 2, and the band within this F1 to F2, where the F1 is the lower half and F2 is the upper half power frequency, is known as the bandwidth. So let's take an example. Here we need to find out the coil of 1 kilo ohm resistance is given, where inductance is also given and connected in the variable capacitor across 2 volt 10 kilohertz supply. We need to calculate the capacitance of the capacitor when the supply current is minimum, and the effective impedance of the network at resonance and the supply current. So using the formula F equal to 1 by 2 pi into root over of LC, we can find out the capacitance C, and that becomes 1.69 nanofarad. And for the impedance Z, that is equal to L by R into C. So by calculating here, that becomes 89 kilo ohm, whereas for the current I equal to V divided by Z, and we can find out the current 22.5 into 10 to the power 6 ampere. So let's take another example. Here bandwidth is given and the resonating frequency is given, and we need to find out the value of Q. R is given and inductive reactance of the resonance is given. Now bandwidth is the ratio of resonating frequency by Q factor. The Q factor becomes the resonating frequency by the bandwidth. From this equation we can find out the XL and XC are same at resonance. So XL become XC, that is also is equal to 120, and X equal to 1 by 2 pi FC. So we can find out the value of C, that is 0.22 microfarad. And here we can take an example where supply voltage is given and RL, that is the variable resistance, is connected with the inductor, that is J10, and here 4 and minus of J5. So impedance Y in this series is equal to 1 by RL plus J10, and we can convert this into by multiplying RL minus J10 in both sides, and similarly YC, that becomes this one. And the total Y is equal to summation of YL plus YC. Now at resonating condition, the imaginary part becomes 0. So we are taking the imaginary part equal to 0. We can solve this equation, and from this we can find out the RL is 4.24. but this value is not physically possible. Next is the applications, and for the applications of the parallel RLC circuit, we can say that the maximum application is in the tuning of the radio, and in radio frequency in circuit designed to produce the AC signal. And we tune a radio wave to a particular station, then LC circuit, and set a resonance for that particular carrier frequency. Usually, a parallel circuit is used for that purpose, with the capacitor and inductor directly connected together and exchanging energy between each other. Just a pendulum, which can be used to stabilize the frequency of a clock. So tank circuit can be used to stabilize the electrical frequency or the AC oscillator circuit. Another use is the load impedance or output circuit or RF amplifier. And in RF amplifier, due to high impedance, the gain of the amplifier is the maximum at resonating frequency. And another are the induction heating. Realistic parallel resonance also can be used as the current rejector. And the series resonance is used for the voltage amplifier. And these are the references. Thank you.